Can everyone hear me?
Yes.
Okay. So what answers did you get for the first question? Okay, I see a few answers in the chat. Are there any other answers? Okay, I don't see the answer that I have, but I see a few answers of 231. So maybe Ahana, can you explain how you got 231?
So from 81 I added 30, but then like since the 50th term since there's like you have to find the 50th one, I did 50 times 30 because I think you're adding 30 each time, which I got 150. So I added 81 to 150 and I got 231.
I see. Okay, so I think one thing that you have to be careful of here is it looks like there's some pattern here, right? 12, 15, 18, 21, 51, 81. And then you want to add, kind of continue this pattern, but you have to be careful that that we want all positive multiples of 3 that contain at least one digit that's a 1, right? So that's how we found these numbers up to 81. So what is the next multiple of 3 that contains at least one digit being a 1? 102, good.
102.
Yep, so 102 is the next one. What about the one after that?
105.
Good. And where does that go up to? So we know that when you're in the 100s, they always will start with a 1, right? So for that set, we can actually say 102, 105 up to 198, yep, are all multiples of 3. But that pattern then stops holding after 198, right? Because then the first digit becomes 2. Then all of them are no longer have a digit that's at least one digit that's a 1. So you have a kind of a special case here between 102 and 198. So now let's keep track of how many have finished. So between 1 and 100, how many multiples of 3 do we have? Should just be 6. We have the 6 numbers here. Now between 100 and 200.
Amen.
We should have 33. Is that correct? So 102 to 198, you keep adding 3. So you can add a 3 32 times plus the first one. So this is a total of 33. So good, yeah, Ishan said 39. So that's this between 1 and 200, 33 plus 6 is 39. So now we've covered 39 terms in the sequence up between 1 and 200. So now what's the next one in the sequence after 198?
201.
Good, 201. What about after that?
231.
So it seems like it. Okay, so we do have 231, 261, 291 are going to be numbers between 200 and 300. But is there potentially something between 201 and 231 here? 210, good. So you have to be careful now that the question is saying that at least one digit is a 1, right? So it doesn't have to be the last digit here. It could be some digit in between, right? So the first digit now is going to be a 2 in the 200s. So the intermediate digit could also be a 1. So that gives us 210, yep, 213, 216, 219. So now how many total do we have between 200 and 300 then, based on this? Close. Let's see. 201. So we have 201, 231, 261, 291. There's 4. And 210, 213, 216, 219 is 4. So we have a total of 8 between 200 and 300. So now how much do we have so far? 33 plus 6 plus 8. So we have 47. So we need 3 more, right? So what is the third one after that? So okay, so what is the first one after 291? 300. Careful. So does 300 have a digit of 1?
312.
312, good. What's the one after that?
315.
215.
315. So which number is this? We have covered 47. So 312 is the 48. 315 is the 49th. So which one is the 50th one?
318.
318. Good. So the correct answer should be 318. Does this make sense? Any questions on this? So you have to be careful when you see the pattern after 100. It does feel like, okay, it should be adding 3 each time, but you can't just add. Once you reach the 200 mark, then it no longer necessarily has 1 digit that's a 2, right? So 201 does, but then 204 doesn't, right? So then I actually have to count the ones in the 200s. There's only 8 of those. Then in the 300s, I can find the last 50th element, which is 318. Any questions on this? Okay, and just quickly to review, what is the rule to check that a number is divisible by 3?
The sum of the digits have to add up to a multiple of 3.
Good. And what about divisibility by 9, just as an extension to that?
The sum of the digits has to be a multiple of 9.
Good. Yep. So it's the same kind of rule. So that's useful in this case, particularly the multiple of 3 check, because whenever you're trying to find if the number ending with 1, for instance, 201, is that a multiple of 3? It's easy to just add up 2 plus 1, 3. Make sure it's a multiple of 3, and it's the number itself is a multiple of 3 also. Any questions on this? Okay, let's go on to the next question. Okay, what answers did you get for this question? Okay, I see a few different answers. 360 is correct. Pavan or Preeti, can you explain?
Okay, so I did 6 choose 2,
Okay.
and then that was 15. Because I had to satisfy the requirements where one guy is in front of the other guy, that leaves 4 factorial for the number of ways we can do all the other spots. So then we just multiply those together, and we do 15 times 24 to find the total.
Good, this works. So let's just go over this in terms of the slots. So you have 6 slots, right? Let's say A, B, C, D, E, F are the time slots, right? So basically what we're saying is that you have these 6 different people who need to present, but there's only one condition, that the Smith's lecture needs to be before Dr. Jones' lecture. Smith's lecture needs to be after Dr. Jones' lecture. So what you can do is you can first try to see, okay, of these 6, let's choose 2 of them that are going to be Smith and Jones. Let's say those are B and F. So once I choose those 2, I'll make sure to put Jones in the first one and Smith in the second one. And then the remaining ones, I can put them in any order. So choosing the 2, there's 15 ways. 6 choices for the first, 5 for the second, divided by 2, or 6 choose 2. And you can multiply then by 4 factorial, which is 24 for the remaining orderings. So if you multiply those, you get 360, which is correct. Now there's another way of doing this that I think is a little bit simpler. You can think about if I consider all possible orderings of the lectures.
That's what I do.
How many of them do you need to remove?
How many? How many of them do you need to be removed? Bailey, how many of them do you need to be removed?
Any ideas? Half. Good. So another way to think about this is I have all the lectures, right? I can do all possible orderings. In half of them, Dr. Jones will be before Dr. Smith, and in the other half, Dr. Smith will be before Dr. Jones. So basically all the possible orderings will be 6 factorial, or basically six choices for where the first lecturer would speak, then 5 for the second, and so on. So this is 6 factorial, and I just have to divide this by 2 to account for that either Dr. Smith can be before Dr. Jones or Dr. Jones before Dr. Smith, and only half of those lectures are possible. You can think about this also alternatively that if I take any ordering, if Dr. Jones is before Dr. Smith, I can convert it to another ordering by just flipping the 2, right? So for every ordering that works, I can create the one that doesn't work by just flipping Dr. Smith and Dr. Jones. That's another way to see that the number that work, that Dr. Smith is before Dr. Jones, is equal to the ones you need to remove. So it's exactly half of the total number of orderings. So this is another way of computing the same value. You can either choose the 2 places for Smith and Jones and reorder the rest, or you can count the total and divide by 2. Does this make sense? So I think the ones who got 15 probably just did the first portion of choosing the 2 slots for Smith and Jones. But you have to consider all the orderings of the other 4 lecturers also. Any questions on this? Okay, let's move on to the last question. Okay, I see a few different answers. 24 is right. Pavan or Preeti, can you explain?
Okay, so the most straightforward way that I did was I just did the prime factorization of 8 factorial. So what I got was 2 to the 7th times 3 squared times 5 times 7 times 5 times 7. And since we're doing n squared, we're basically just trying to see which things we can take a square root of. So 2 to the 7th, the most you can take out is 2 to the 2 cubed. And for the 3 squared, the most you can take out is 3 to the 1st. So that's 8 times 3, which is 24.
Good. So yeah, I think the easiest way here to see, basically you want to say something squared should be able to divide 8 factorial. So you want to, if you take the prime factorization of 8 factorial, you can then think about, okay, what is the largest number that I can square that will still divide 8 factorial? So let's do the prime factorization. And one trick to do the prime factorizations of these factorials is to think, okay, so if I want to find the number of times 2 appears in this factorization, I know 2 will appear in 2, 4, 6, and 8 once. So that's 4 times. Now 2 appears extra times in multiples of 4, right? Multiples of 4 have 2 factors of 2. So 4 and 8, that's another extra 2 times that they'll appear, the factors of 2. And then 8, that's a 2 to the power 3, so that's an extra 1 time for the factor of 2. So if you add these up, you see that there's 7 factors of 2 in 8 factorial. And then for 3s, you can see that 3 and 6 are divisible by 3, so there's 2 factors of 3. And then 5 and 7 are also factors, and multiplying 1 through 8. So we have a prime factorization. Now we want to say that some number squared should divide this. So what is the largest power of 2 that would work? So we see that 2 to the power 3, if I square that, that's 2 to the power 6. So that would still divide 2 to the power 7. But if I take 2 to the power 4, that wouldn't work. So 8 works here. In 3s, we see I could take 1, 3 works because there's two factors of 3 and 8 factorial. 5 and 7, there's only one of them in the prime factorization. So I can't actually take something squared and be divisible by 8 factorial. So that basically leaves us with 2 to the power 3 times 3. So that's 8 times 3, or 24. So I think I saw some answers of 12. I think it was likely just missing that we could do an extra 2 here. You had the 3 and 2 factors of 2, but you can actually take 3 factors of 2, square it, get 6 factors of 2, and that still divides 8 factorial. So in general, this is also somewhat similar to there's problems that ask how many zeros are at the end of some number factorial. This is somewhat similar, so you can try to do the same idea. So you can try this as an extra homework problem of if you say something like 2020 factorial, how many zeros are at the end? So an idea very similar to this should work, where you want to find the prime factorization. But when you ask how many zeros, you then want to know how many factors of 10 are there in this. So how many factors of 5 and 2 are there, and you can use that to find the number of zeros. In this case, we use the prime factorization to find squares that would go into the number. But in either case, you want to get some information on the prime factorization of a number factorial. Any questions on this? Okay, then that's it for today's class. We finished a little bit early, and we'll see you all next week.
Thank you.
Thank you.
You're welcome.
Thank you.
Thank you.
Thank you.
Mhm.